All right, good evening, everyone. It's my pleasure to introduce Dr. Grace Wolfe-Chase from the Adler Planetarium, an astronomer, so not a chemist, but I think you're going to find a lot of overlapping topics of things that we care about. She earned her bachelor's degree in physics from Cornell University before doing her Ph.D. in astronomy at the University of Arizona. She then spent time at both NASA's Ames Research Center and the University of California at Riverside as a postdoc before landing her current position at the Adler Planetarium. She's worn many hats while at the Adler. She has had affiliations in the past with the University of Chicago. She continues to have a standing affiliation with the Zygon Center for Religion and Science that I'll get back to here in a little bit. And she really has a very rich career in trying to understand how stars and other planetary objects are born, so to speak, by tracking molecular species. Early on in her career, she was looking at carbon monoxide and carbon monosulfide, molecules that we as chemists sit there and kind of scratch our heads and go, that's not perhaps the most interesting of molecules, but because they're very small, they tend to have very distinct spectroscopic signatures that we can keep track of even at very, very far distances away from the Earth. More recently, I believe she's moved on to study molecules that are a little bit bigger, polyaromatic hydrocarbons, something as large and as scary as formaldehyde. And so I will let her go through all the details, but what she gets out of spectroscopy is very different. We tend to use it as a tool in the lab to say, did I make what I think that I made? Instead, they know what's out there, but they can use the fact that it's out there to actually track how these large celestial bodies are forming or the dynamics of them, which is a very interesting take on the techniques that we are familiar with, but applying them in a very different way. On top of all this fantastic science, she really has tried to bring together the religious and the scientific communities, and so she's currently the vice president for the board of directors for the Center for the Advanced Study in Religion and Science. Hopefully I didn't mess that up. So if it wasn't enough that she's working at the planetarium, interfacing with the public on a daily basis, she's making sure that the religious community is in constant contact with the cutting edge science that's taking place. She also involves the public in her research, which is something that she's going to be talking about tonight, and that there's some information up here about. She has told me that we chemists are sorely lacking in this area, and so we really need to find some projects to get involved with that. With that being said, I think I've taken up enough of her time. Please join me in welcoming Dr. Grace Wolfe-Chase.
Thank you so much, Richard, for inviting me, and I'm really happy to be here tonight. Thank you, everyone. So yeah, that was quite an introduction. Since Richard already described my position at Adler, I'm going to summarize it by saying we try to bring the process of research to the public, and one of the ways we do that is by inviting people from all walks of life to do science with us through something called citizen science, and I will tell you a little bit more about that later. We're switched over. And by the way, there is a wonderful NASA Spitzer Space Telescope selfies app. If anybody wants that link later, just ask me about it. You too can be an astronaut in front of beautiful astronomical nebulae. So pretty much everything we know about how stars and planets form, we've learned since the 1970s, so within the past 50 years. I've been part of that journey since the 1980s. I'm an observational astronomer. Yeah, did I hear a wow? So I've been involved in various aspects of observational infrared and radio astronomy since the 1980s. So I'm hoping to give you something of a personal perspective and journey tonight as we talk about sort of how we've, the broad details of how we've assembled the current picture we have of how stars and planets form. So I'll just start with a brief outline. I'm not assuming people have a background in astronomy. I will start out by giving you a little bit of a background in what you sort of need to know to understand the rest of the talk tonight. And then we'll talk about the discovery of where in space stars are born in entities we call giant molecular clouds. How we have learned over the years that stars and planets form together. We expect most stars to have planets, And guess what? The searches for what we call exoplanets, worlds orbiting other stars, is finding out the same thing. So we currently think that there may be more planets than there are stars in the observable universe, which is really exciting when we think about the search for potentially habitable worlds. And then I'll talk a little bit about how we also have learned that stars and planets don't generally form in isolation, but in clusters with lots of siblings, and how citizen scientists are actually helping us learn about how these early stages of how star clusters form. And then maybe, if there's time, some outstanding questions we're addressing today. So, only 2 slides that are really, really difficult to see from the back, and the rest I think you won't have a problem with. So this shows you basically a schematic of our solar system, roughly 10 billion miles in diameter. The sun and basically a bunch of worlds that orbit the sun. Most of the major planets orbit in a plane, but there are also lots of icy objects out beyond the orbit of Pluto that don't orbit in a plane. The sun and the Earth are right here. They're separated by roughly 93 million miles. It takes light 8 minutes to cross that distance. So another way of looking at it is that the sun is 8 light minutes away. That'll become important when we go out to larger and larger scales. Now, ideas about how our solar system was born, scientific ideas, go back at least until the 18th century. Astronomy tends to be what we call a theory-driven science. And what that means is that there are a lot of things in astronomy, in the universe, that were predicted to exist before they were actually observed, just based on known laws of physics. And a great example of this is the birth of our solar system. So back in the 18th century, Immanuel Kant and Pierre Laplace had an idea called the nebular hypothesis, where they posited that the sun and planets started out as a rotating large cloud of matter in space. And because it was rotating, as gravity pulled it together, it flattened out, and the sun formed at the center where the material was spinning the slowest, and over time, gradually, the planets built up in what we would now call a circumstellar or protostellar disk around the young sun. Now, this explained a couple of observational features about our solar system, that the planets lie more or less in a plane. They orbit the sun in the same direction. But of course, this was an interesting hypothesis that we had no way of testing this back in the 18th century. And even now, of course, we can't wind time backwards and observe the birth of our solar system. What we do have the ability to do now is look out in space at places where these processes are actually going on today. And we can also explore our solar system for some hints as to how our solar system formed. Now, spectroscopy, astronomy uses sort of 2 modes of operating. 1, taking images, 2, taking spectra. Spectroscopy applied to astronomy was born in the 19th century. And in fact, this gentleman here, Father Angelo Secchi, was the first to build a spectroscope and pass starlight through the spectroscope and classify different types of stars by their spectra. And this was important because Secchi realized that the patterns of lines you see in the spectra of different stars give hints to the composition, although he had no theoretical framework for understanding how these lines were produced. With quantum mechanics in the 20th century, we developed a much better understanding of how light and matter interact. And that's why I have a portrait of this woman here, Cecilia Payne-Gaposchkin, who some say did the most brilliant dissertation in astronomy in the 20th century. She was able to relate spectra and stars in the sun, and not only relate to composition, but also to temperature. She's the person responsible for positing that stars are actually big balls of hydrogen for the most part. So the joke I shared earlier to astronomers, hydrogen and helium are the major components of Norman matter in the universe, and the rest of the stuff on the periodic table we just refer to as metals. And I know to you chemists it's ridiculous, but that's the way we think about it sometimes. So if we go out to look at what we would call the solar interstellar neighborhood, and now we're looking at a region about 30 light years across, centered on the sun, looking out at some of the brighter stars, this by no means all the stars within 30 light years of the sun. But I wanted to show this. So again, 30 light years, light travels 6 trillion miles per year. That's a very large number in miles. We often use light years when we talk about interstellar distances. Now, stars come in a variety of colors, which are related to their temperatures, an enormous variety of sizes, masses, and brightness. And by brightness, I don't mean how bright they appear in the sky, but how bright they would appear if you could line them all up at the same distance. So around 70% of all the stars out there are stars that we call red dwarfs or M dwarfs. 50 of the 70 nearest stars are M dwarfs. You can't see them, they're too dim. These stars are tens of thousands up to 100,000 times dimmer than our sun. Again, if you could compare them at comparable distances. On the other side of the spectrum, we have stars we call O and B stars, bright blue luminous stars that the O stars comprise very much less than 1% of all the stars out there. They're very rare, but they're very important because stars are nuclear furnaces. During their lifetimes, at their cores, they fuse together mostly hydrogen into helium, but heavier elements as they age, until the most luminous, the most massive stars can fuse together elements as heavy as iron, and after that, you don't get any energy out by fusing anything heavier, so the star has a catastrophe, and it both collapses and explodes into what we call a supernova. So these supernovae, I wanted to mention them because they're essential for distributing heavy elements through space. In fact, pretty much all of those elements on the periodic table, heavier than iron, were synthesized during supernova explosions. I say pretty much because there are some exceptions. Some of those things come from other objects in the universe as well. But so these are really important. These very luminous stars are very important. We want to understand them. They're very important to understanding how the elements arose. So going out a little bit further to a beautiful winter constellation of Orion, the nearest star-forming region that contains bright O stars is what we call the Orion Nebula. It's also what we call an H2 region, in this case, H, capital I, for ionized hydrogen. The reddish color from nebulae like this come from recombination of hydrogen atoms. In particular, the reddish color comes from a spectral line called Balmer alpha. And this is, or called hydrogen alpha, excuse me, one of the Balmer lines. So what you're seeing here is very hot gas lit up by very, very luminous stars at the center here. Now, this nebula is about 3 million years old, and we're going to come back to this in a little while. So going out even further away, by the way, that nebula was at a distance of about 1,300 light years. So we're going out to bigger distances. On the left here, we have a beautiful view of the Milky Way from a radio telescope array called CARMA in not Chicago, in California. And yes, there are places in the world where you can still see the night sky like this. This is the view that we infer our galaxy would look like if we could travel outside. We can't do that. Our galaxy is about 100,000 light years in diameter. We build up this picture by making measurements with various telescopes of various kinds of light from within our place orbiting the sun in the suburbs here. So the sun is about halfway out from the center of our galaxy here. And again, this is the number in miles. So it's kind of cool when you look at the stars next time, remember that you're looking into the past. Because the further away you look, the further you're looking into the past, because it takes light that long to cross these distances. So moving on here, the birthplaces of stars are actually these dark places in the Milky Way that you don't see because they're dusty. And they block the light from visible stars within the plane of our galaxy. So you can't read the yellow very much, but it says the cold birthplaces of stars were discovered in the 1970s using microwave telescopes. So telescopes that operate at millimeter wavelengths, sort of what you would call short radio here. And this telescope in particular was very instrumental to detecting a lot of different molecules in space. So let's look briefly at spectroscopy in astronomy. So this old figure just highlights the fact that whereas in the visible light, a lot of emission lines we see are produced by electronic transitions. At colder temperatures, where you have molecules, we get a lot of infrared and radio wavelengths out of corresponding to rotation and vibration of molecules, and that's just sort of what's being illustrated here. Just like those electronic transitions, rotational transitions and vibrational transitions are quantized. So you get out energy at very, very specific frequencies when these molecules emit. And I'm telling you this to set you up for the next slide about the discovery of giant molecular clouds. And actually, they didn't know what they discovered at the time. So this is actually the title page from a very short letter to the Astrophysical Journal by Wilson, Jeffords, and Penzias that says, carbon monoxide in the Orion Nebula. We have found intense 2.6 millimeter line emission from 9 galactic sources, which we attribute to carbon monoxide. So very kind of unexciting here. This is one spectral line corresponding to the lowest rotational transition of carbon monoxide at about 3 millimeters. And throughout the 1970s, a lot of millimeter wave telescopes were very actively mapping out the extent of these molecular clouds, and some of them are about 100 light years across. Now, CO is the second most abundant molecule in the interstellar medium. Molecular hydrogen is the most important, but here's the caveat. Carbon monoxide emits dipole radiation. H2 doesn't. It's a symmetrical molecule. And the transitions that excite H2 tend to be at hotter levels of infrared observations. So we use CO mostly as a proxy, one way of inferring using abundance ratios, inferring molecular hydrogen. Carbon monoxide is excited at very cold temperatures, this low rotational transition, and at pretty low densities, where we're talking like 1,000 particles per cubic centimeter or less, or per, yeah. So low densities, low temperatures. Now, one thing that's kind of interesting on this spectral line here, which isn't very exciting at all, you might notice there are these broad line wings. So these spectra give us information not only on the physical properties of, for example, molecular clouds, but on velocity as well through the Doppler effect. And so initially, people thought that these broad line wings were maybe an instrumental artifact. But after mapping out the extent of these molecular clouds, they noticed that very often you found shifts that were parts of the lines that were line wings that were red shifted and blue shifted around very bright infrared point sources. Now, you might get a kick out of hearing that this is from an old transparency view graph from a talk more than 30 years ago, about 35 years ago, so that's why it's marked up like this. This was an early model of what we now call a bipolar outflow around a very young protostar. Now, at the time in the 1980s, we were not observing infall onto the star. We weren't observing these disks. These disks are very, very small, like less than or about 1,000th the size of these bipolar outflows. I think I neglected to mention radio telescopes have very poor resolution. The resolution of a telescope goes as the wavelength over the diameter of the telescope. So a telescope operating at millimeter wavelengths has a resolution of about 1 minute of arc on the sky, whereas an optical telescope about 1 second of arc. So the optical telescope has like 60 times better resolution. So it's very, very difficult to observe the fine details of what's going on. Basically, all that they observed was a bright, invisible infrared source with indications that there were these huge outflows of gas in both directions. We sometimes use parsec instead of light years. This entire outflow from this little protostar is about 3.26 light years in diameter. That's nearly the distance between the sun and the next nearest star. So these are huge, huge distances. And when I started graduate school at the University of Arizona, my advisor, Charlie Latta, had initiated a big program to basically look for these, to look for the signatures of these bipolar outflows around these infrared sources in molecular clouds. So I was fortunate to be in on some of the very early work here. This gives you an example of the extent of one of these molecular clouds called the Monoceros OB1. That's OB1, not Obi-Wan as in Star Wars. The OB stands for an association that contains O and B stars, those very, very luminous stars. And I just wanted to give you an idea of where this is on the sky. Monoceros isn't a terribly exciting constellation. Orion is pretty neat. But this entire area here is about the width of a full moon and about 4 full moons in length. At the distance of this cloud, which is about 800 parsecs away, this is almost 100 light years in extent. So what you're seeing here is just an old photographic plate seen in negative black and white, reversed from an old red. So the black here is just sort of some optical nebulosity. And this contour here indicates where most of the carbon monoxide, where you find most of the emission of the carbon monoxide in this cloud. So that's a cool little representation of Monoceros from our historical collections at the Adler from the 19th century. So in 1992, I did my Ph.D. dissertation on this cloud. And instead of studying the large-scale CO properties, I looked at what we call the dense cores around some of these very young infrared sources that were driving outflows. And I just wanted to tell you how we used to do things. I hate doing this, how we used to do things in the old days, but this will give you a sense of how difficult it was to do this back even as recently as the early 1990s. We used to actually move radio telescopes to different positions on the sky and take one spectrum. So you guys probably are used to seeing lots of spectra. So there are 2 different ways you can set up a spectrometer. You can set up a spectrometer to get a bunch of narrow lines with very low spectral resolution, but you can get more than one spectral line. Or you can set up the spectrometer so that you get very high velocity resolution, but you sacrifice bandwidth. So in this case, we were very interested in the line profiles, in what was going on to study the dynamics of these cores. And we actually, one of the results of my dissertation was that we found even more gas than we thought that was being entrained in these huge outflows from these very, very young stars. So these dense clouds where stars can be born are about 100 trillion times less dense than air. So on that note, so this is, Richard mentioned carbon monosulfide. So carbon monosulfide, this is not the lowest rotational, the second lowest rotational transition, and the CS molecule happens to be excited at high densities, these transitions, so it's a very good tracer for the densest parts of these clouds where the stars are actually born. So just for fun here, I wanted to do a comparison of molecular clouds and atmospheric clouds. And you'll notice here how incredibly different the scales are in size, in mass, in particle density, molecular atomic weight, okay, guys? Hydrogen and helium and everything else is a metal. So we have these things very low molecular atomic weight compared to atmospheric clouds. What's interesting is that the speed of sound is roughly comparable, and that's just because sort of the temperature and the atomic weight kind of go in the same order of magnitude difference here, so the speed of sound kind of comparable. Just an interesting thing to add. So within these giant molecular clouds, we have very scientific names for different aggregates of things within molecular clouds. We have clumps and cores. And these structures are not very, very well defined at all. The parts of the cloud that are dense enough to form stars are called cores, and clumps are generally aggregates of cores that you find, well, clumped together, hence the word clump. But you can see here that the mass of these cores compared to the mass of the giant molecular clouds, the densities, these are very, very different. And in fact, the cores are a very small fraction of molecular clouds. So you've got these big molecular clouds, but stars can only form in actually very, very small regions of the molecular cloud. So by the mid-1990s, we had put together a picture of how stars and planets form by making lots of observations over lots of different wavelengths. I do want to note that at the time this picture was put together, we were still 2 years away from actually detecting these disks around young stars. And in fact, just last year, and I'll tell you about that at the end of the talk, we've got the first evidence of planets building up in a disk around another star. So that's really kind of cool. These time scales are very, very, not terribly accurate, just order of magnitude. And they're based both on theoretical models and on statistical studies by observing stars in various stages across a lot of different star-forming clouds. So, let's see if there was something else that I wanted to mention about this before we go on. So I have another way of looking at this here, and don't worry about these classes. This is not really relevant to the point I wanted to make here. I'm showing you this because I wanted to show you the spectral energy distributions of these different objects. What's a spectral energy distribution? It's just the flux coming off of this object, the energy coming off over a whole lot of wavelengths. So for example, the very early stages, okay, basically, you don't see them over here in near-infrared light or optical light. You only see them at wavelengths that correspond to what we would call mid-far infrared and millimeter wave radiation. So it's not until these stars have actually cleared out some of their cores with these outflows where you actually can see a visible star eventually. So we have another ingredient besides gravity in star formation. And yes, if you're wondering, I was a competitive figure skater eons ago. I didn't have a picture of myself spinning here, so just stuck with a couple of old photos here. So the rotating clouds that have to collapse down to form stars are about 1 million times larger than the stars that they form. So what happens as these spinning clouds collapse down? Well, they spin faster and faster. And in fact, it was a problem for many years figuring out how you can get a star to build up at the center if the cloud is spinning so fast. Well, it turns out that gravity isn't the only important ingredient, as was sketched out 200 years ago, but magnetic fields are everywhere in space, and they get pinched together as stars form, and these magnetic fields actually thread through these protostellar disks and launch matter from these disks, basically slowing down the spin of the disk a little bit to enable the growing star to form. But we needed infrared and radio telescopes to put together this, this picture. And one of the neat things about these outflows is we now think that wherever you see these outflows, you have some sort of accretion disk. That happens at the centers of galaxies, like these large accreting disks around black holes. So these jets and outflows are often used to infer the presence of a disk, even when you can't see the disk directly, because it's so much smaller than these outflows. So I wanted to show you a few of these beautiful jets in star-forming regions. These were assembled, all of these things here are invisible, except for the stars. These were assembled from near-infrared and mid-infrared observations. 2 of them were actually from publications, my earlier publications, some 10 and 20 years ago. And I just wanted to show you because these are just such beautiful objects. So these are these jets that are observed in near-infrared and mid-infrared light. We do think that they are associated with the outflows. They may actually sweep up the outflows. We see them at these wavelengths because as the winds come off of the disks from stars, they shock the gas. They heat it to very, very hot temperatures. And so you get transitions from atoms and molecules that are excited in that shocked gas. So just a couple of fun facts you can share at your next cocktail party. Protostellar jets launch about 1 trillion tons of gas into space every day. And the jets that are launched in this manner travel faster than 1 million kilometers per hour. Cool facts. So, that's the general picture for how one solar-type star can form. Unfortunately, there's a big complication. We have learned, well, I wouldn't say unfortunately, I'll just say that there's a big complication here in that we've learned through the years that stars are born and they grow in community. They're not born one star at a time, but clusters with a great many stars. So what you're seeing here is from a very large survey that I did a few years back. And I used near-infrared observations to detect some of these jets in regions that are known to be forming massive stars. And what you get is a picture of different things at different evolutionary stages. So for example, over here, the colors here, by the way, are using the ratio of 2 vibrational transitions of molecular hydrogen. Near-infrared around 2 microns, near-infrared light. And by ratioing these lines, we can distinguish between the kinds of shocks you find in jets and what you find in this little cocoon around this young cluster of stars. These stars are invisible in optical light. You only see them in near-infrared light. And this little cocoon is what we call a photodissociation region. So this is where both you get hydrogen separating from molecular into atomic, and also recombining and fluorescing. And that's how you get these colors that you see around this very, very young cluster of stars. So that brings me back to the Orion Nebula. And here's a Hubble Space Telescope view from the mid-1990s. And it's even more complicated than gravity plus magnetic fields, because in regions like this, you have radiation from the very, very hot O stars at the center here. You have turbulence in the gas. So it's challenging to figure out how regions like this come to be. And by the way, the Hubble Space Telescope has very good resolution, about 1/10 of an arc second. So that's better by a factor of 10 than ground-based optical telescopes. And these little dark objects in the foreground are approximately the size of our solar system. And we've studied them over the past 25 years. And there's very good evidence that what these are planetary systems in the process of forming today. But these stars and planets form through processes that play out over an enormous range of scale in time and space. You're looking at a few light years across here. The entire Orion Nebula cluster is about 20 light years across, containing 2,800 stars. And we do think that our solar system formed in an environment like this because there's evidence that a supernova explosion happened close to our sun and its planets when the planets were first building up a long time ago. We think most stars, in fact, form in environments like this. So how do we study this? How do we figure out what's going on and where regions like the Orion Nebula come from? Well, first of all, I'd like to look to a beautiful external galaxy. In addition to our Milky Way, in the observable universe, there are several 100 billion galaxies of stars. This is one of the nearer ones at a distance of about 23 million light years. And you can see all of these dark regions. These are these dusty places that contain lots of molecular clouds. And then these fuzzy red patches highlight the H2 regions, the regions of ionized gas around the birth of the most luminous stars. But this galaxy is far away. We can't study the details of these features. We have to look to our own galaxy to study in detail. But here's the problem. The problem is the plane of our galaxy is dark. It contains all this dust. You can't see through it visibly. You can penetrate it in infrared light. So this is a small section of a very large survey with the Spitzer Space Telescope cut out from the direction towards the center of our galaxy. And here, we're not looking at narrowband images. So we're not looking at spectral lines. We're looking over a broad array of wavelengths. But as Richard mentioned earlier, there are a lot of complex molecules that have been identified in space, including long chains of hydrocarbons known as polycyclic aromatic hydrocarbons. And it turns out that in this 8-micron band, there are a lot of features from these PAHs. So actually, most of what you're seeing here in green comes from these polycyclic aromatic hydrocarbons. Now, when I say green, of course, I don't really mean green. Here we're using blue, green, and red to represent these different wavelengths. And I know you can't see this from the back of the room, but this blue background that looks like a uniform blue background, if you got up real close, you'd see it's comprised of a whole bunch of little pinpoints of light. It looks like a sandbox, and that's because you're looking through our galaxy to the other side, a distance of about 75,000 light years. So everywhere your eye intersects a star in our galaxy, even though they're separated by enormous distances, it looks like they're terribly crowded. So in infrared light, we can peer through that dust, and we can also observe cold gas and dust that doesn't emit at optical wavelengths. So this is part of a few legacy surveys by the Spitzer Space Telescope. And here I'm back to our model of the outsider's view of our galaxy to show you where the survey was taken. So here's our sun. The Spitzer Space Telescope, over hundreds of hours of observing time, observed basically 1/3 of the way around our galaxy, the inner galaxy, and 2 regions further out so that we could compare star-forming properties in the outer galaxy to the inner galaxy. So this feature here is basically what a young H2 region looks like in mid-infrared light. We call this a bubble. It's produced as hot luminous O and B stars start to heat up their environment. There's also ionized gas within here, as well as very small grains of dust, basically like large molecules. And then these features always have these bright green rims where you get emission from the transition to mostly ionized gas to mostly molecular gas, and you get these PA features excited, these polycyclic aromatic hydrocarbons. Thousands of these bubbles scattered through the plane of our Milky Way. We want to take a census of this. We want to know how many of these massive stellar nurseries there are in our galaxy, because we need to know that to know how they influence the evolution of our galaxy. We needed the help of people to classify these things. So now I'm finally getting to talk a little bit about citizen science. My overlay, I almost forgot. So even though there's generally one or a few stars that are bright enough to actually light up the gas like that, these massive stars don't form alone. We have lots of evidence that these features have much lower mass stars. You don't see them in these kind of images, but we have good reason to believe that there are clusters that accompany these bubbles. So there's more than one star in most of these bubbles. So I will say it takes a community to do big science. Citizen scientists extend the reach of what scientists can do. One of the really cool things where we suffer from is an overload of data and images these days, and that's a good thing. But very often, we need a lot of eyes inspecting some of these images, in some cases inspecting them for things that machines are not very good at pulling out. So the Adler Planetarium, together with the University of Oxford, has developed a web platform called Zooniverse. And if you find anything that I'm going to be saying over the next 15 minutes or so interesting, by all means take either some of the stickers or some of the handouts I have here, because this is a great way to participate in a range of different research projects. As Richard mentioned earlier, sadly, we don't have chemistry represented, but we have just about every other science at this point in time, as well as humanities projects that have people looking through digitized texts to pull out information. This is a great way of having people around the world, exposing them to the process of science, helping the researchers really do science projects we couldn't do without their help. So we crowdsource their abilities, their energies to help us do science that we wouldn't be able to do otherwise. So Zooniverse is this growing repository of citizen science projects spanning many fields of academic research. More than 1.7 million people around the world participate. And in 2005, we launched a tool called the Zoo Builder. So now researchers can develop their own large citizen science projects and work with us at the Adler, the University of Oxford, to get them launched on the public site. So this is just kind of fun background wallpaper highlighting some of the bubbles that were identified by citizen scientists. They cataloged more than 4,000 bubbles working on a project called the Milky Way Project that I'm on the science team for. Across the Zooniverse, there are currently 90 active projects that have resulted over the years, in the past 10 years, in 192 peer-reviewed publications in very prestigious journals. So these projects are producing really excellent research. So while the citizen scientists were finding bubbles for us, they started chatting about some of the things we didn't ask them to find in the images. And so all of the projects come with social media like blogs and talk forums where the citizen scientists can talk to each other as well as the team researchers. So this is a great way for them, if they're interested, to get more information about what we're doing with the classifications they're making for us. And there were, early on in this project, people started to chat about these sort of circular yellow objects that were hashtagged yellow balls, and the name, unfortunately, has stuck. But this is a great example, I think, of, I love this quote from Isaac Asimov. So Isaac Asimov was a 20th century science fiction writer and biochemist. And he writes, "The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny." So one of the great exciting things about citizen science is people get really drawn into these projects and they get very curious and they want to explore further. So we added tools so that they could catalog and measure these yellow balls for us. And over the course of the past several years, the Milky Way project has now identified more than 6,000 of these so-called yellow balls. So what are they? What are yellow balls? Well, we have hints from the digital images. You get yellow color in these digital images where the red and the green overlap completely. And most of the red emission comes from warm dust. Most of the green comes from those polycyclic aromatic hydrocarbons. So our hypothesis was that these yellow balls represent a very, very young stage, early stage in the production of these bubbles. When the stars just start to interact with their parent clouds. Why was this exciting to us? It was exciting because star formation studies have suffered from one big problem. Either the star formation region is already so evolved so you can see the stars, but the birth cloud has gone away, has been dispersed by radiation, winds, and bipolar outflows. Or basically what you see is a dense cloud and no stars in there. With yellow balls, we actually have a stage now where we can see both the star content as well as these clouds. So these clouds, these yellow balls at mid-infrared wavelengths, you can see in the center here, you can actually see the stars inside at 2 microns. And these yellow balls are also associated with clumps of gas, really cold gas that we can see at millimeter wavelengths. So we have the opportunity here, we have a database now to peer into these things, to actually see the development of very, very young stars. And this is a good example of what you see in astronomy depends upon the wavelength you're looking. And it also shows you some of the difficulty if you want to tell a complete story in astronomy, how you choose to represent your data. I can't show you everything from gamma rays to radio waves, so we have to pick and choose to highlight what is important, what we're trying to get at, what we're trying to learn. So some of the things we can learn from these yellow balls, infrared, microwave, and radio wavelengths certainly provide us the most useful information. And fortunately, there are now galactic plane surveys that cover all these wavelengths. Distances are critical. Without distances, there's only a few things we can do. We can do photometry. We can measure the light emitted at different wavelengths, and that gives us information on temperature and something called color. It gives us a slight indication of the composition of these objects. But with distances, we can calculate things that are far more interesting to astrophysicists. Important things like the physical size. You can measure an angular size, but without the distance, you don't know the physical size. We can also estimate the mass, the brightness of the luminosity coming out of these things. And one of the reasons this is really important is if we can measure the luminosity, that sort of gives us an upper limit to the kinds of stars that are forming in there. So we're hoping to be able to use yellow balls to distinguish the regions that are going to produce these really massive luminous stars from those that aren't. So we have a unique opportunity to peer in to the infant stage of star formation here. So in our first paper, we started with a very, very small sample of these yellow balls. And by very, very small sample, I mean 138, where we had distances, and oh gosh, yes, this is terrible. You can't see that graph at all in the back of the room. But basically what this shows is that most yellow balls are less than a parsec in diameter. That's less than a few light years across. In fact, there's a lot of them that are much, much smaller than that. So these are very, very compact objects. And these are very, very compact objects that have the brightness of the kinds of stars that we're interested in. So again, I apologize. I didn't realize this slide would be so washed out. But this is a histogram showing how many yellow balls fall into different bins of luminosity. These tick marks here, 03, 05, 07, 09, B0, represent different kinds of stars. These are the brightest stars. Out to B2 here. B2 and above, those are the stars that eventually, at the end of their lifetimes, can produce these supernova explosions. Now, there's a caveat. These actually give us an upper limit to the most luminous stars, because if you remember earlier, I told you a lot of these yellow balls contain more than one star. Fortunately, many of them contain one whoppingly bright star. So this is actually probably a pretty good indication of the brightest star in these yellow balls. How am I doing time-wise? Am I good, Richard? Okay, all right. So in our first paper, again, we sort of sketched out a visual sequence for how you go from a very dense, dark, infrared dark cloud to one of these more mature, shall we say, bubbles, H2 regions. And again, these are very, very rough timescales, going from 10,000 years to 100,000 years to roughly 1 million years. The Orion Nebula is a little more evolved, about 3 million years old. And so this was the sequence that we proposed in our first paper, but we didn't have a very large sample for this first paper, and we really want to know whether all of these will actually turn in to full-fledged H2 regions. So to address that question, we had to start working with a much larger sample. Before I get there, I want to do a quick aside. Any of you have kids? I know Richard has a month-old daughter, so she may not be reading this quite yet, but there is a wonderful academic journal called Frontiers for Young Minds. And this is a journal that is geared for kids from 8 to 15 years old. I know that's a pretty broad range. The articles are written by researchers who have published in journals, so in peer-reviewed journals. The articles are reviewed by students and in some cases their teachers. And when I say reviewed, what they review them for is clarity. So if you write up your research, the challenge is to make your research accessible to kids as young, perhaps as 8 years old. And very often they tell you go back and do it again. Kids are great that way. But this is a wonderful journal, and you can see that there are a number of fields that are represented. No chemistry. If you want to write up some chemistry articles, contact these people at the journal. Go to Frontiers for Young Minds and start a chemistry sequence. I think this is a great idea. It gets kids exposed to academic research very early on, and they get pretty excited. If I have time really quickly, I just wanted to say, give you a little story about one of the early neuroscience. We were invited to write the first astronomy and space science article Probably because it was a discovery by citizen science and also because of the cutesy name. We had a lot of media attention when we published our paper because of that name, Yellow Balls. There were reporters that were writing articles entitled Discovery of Yellow Space Balls, and we thought that maybe, you know, Mel, what's his name? What's his last name? Brooks, thank you, as opposed to Mel Torme, yeah. Mel Brooks was going to be contacting us, but he never did. But anyway, yeah, so this is the first field of science represented in this journal was neuroscience. And there was a classic comment from a third grade boy who was scratching his head, who reviewed one paper and said, you know, this seems like a really interesting paper, but I doubt anyone in the third grade knows what a power spectrum is. So, so that was one of the go back and do it again examples. So my colleagues and I've listed some of my colleagues up there, are now working on a second paper based on a much larger sample from that yellow ball catalog that was produced just recently. And we're doing a much more rigorous quantitative analysis. One of the things we're doing is fitting two-dimensional Gaussians to the flux coming from these yellow balls, and we're able to quantify the size much better doing this. We find that the user-measured sizes are, for the most part, bigger than these things. So these are very, very compact, very compact objects. We're also calculating the distance to a larger number of these yellow balls. And here's how we do that. I told you these yellow balls are embedded in molecular clouds that we can actually associate with molecular spectra taken from other surveys. Now, there are models of the rotation of our galaxy. So basically, everything orbits the center of our galaxy at different speeds. And from the velocities of these molecular lines, you can use that information from the spectral lines to determine pretty much where that cloud is in the galaxy. Now, there's a little bit of ambiguity because through some lines of sight through the galaxy, you can have things at a near distance or at a far distance that have the same projected Doppler shift. But sometimes we have additional information to improve those distant estimates. But now we can do this for most of the yellow ball catalog, so we have a truly huge sample of these objects. So one of our questions, I am sorry, I don't know why this is so washed out. Can you see this at all? From back there, you can. I can't from up here. I can see it on my laptop, but can't from. So our old histogram of luminosity is sort of over here, and our new histogram is over here. And now we're going out to what we would call later B star luminosities, B3, B5, B8. These are what we would call intermediate mass stars. These stars do not produce supernova explosions. And so one of the really cool things about this is that we scratched our heads because there were so many more yellow balls than there were these bubbles. But the time scale for this phase should be about 10 times shorter. So you would expect to find fewer of these objects. Well, the reason you don't find fewer is that a lot of these objects are producing lower mass stars, which is incredibly exciting for us because now we have the wherewithal, we have a list of objects where we can actually compare how different types of stars actually form. So here's the cutoff for stars to the right that are luminous enough to form supernovae. I think this next plot it's very detailed, and I think that I'm not going to say a whole lot about this. This is an evolutionary sequence, an evolutionary plot. It's a little bit difficult to explain. We have luminosity on the vertical axis, mass on the horizontal axis. And the upshot is stars that have sort of arrived, mature stars that have cleared out their environments, should fall along these horizontal tracks. And everything over here between these two lines is represent objects that are still accumulating mass. So we were very excited. This was another piece of confirmation that these yellow balls are very, very young objects that are where the stars are still accumulating mass and evolving. So that brings me to the final part of my talk, exploring outstanding questions today. There are lots of instruments I could talk about. I chose to talk about the Atacama Large Millimeter Submillimeter Array in Chile, because this is an incredible instrument. It's an array of radio telescopes, 66 radio telescopes, about 54 of them are 12 meters in diameter, like that old single dish I showed you at the beginning of my talk. 12 of them are slightly smaller. And what this is an interferometer, and I'm not going to explain interferometry tonight. Suffice it to say that you can link these telescopes together so they simulate having a huge telescope, basically the size of the separation between all these telescopes. So you get incredibly high resolution, like resolution that's as good as or much better than the Hubble Space Telescope, only at millimeter and submillimeter wavelengths. They're located at a high and dry location in Chile, so high you can't go up there for more than a short period of time, and you need oxygen. And there's very minimal water vapor to absorb at these wavelengths. At submillimeter wavelengths, our atmosphere absorbs a lot of the millimeter, the submillimeter wavelength coming from space. So, you know, this resolution, compare that to the resolution of a single antenna of like 1 arc minute, and this instrument just enables us to study the fine details of what's going on as stars and planets assemble. So one of the things my colleagues and I are planning to propose in the near future is ALMA can use transitions of carbon monoxide, but there are other molecules as well, to actually study the motions of gas within these yellow balls, to actually see how these stellar embryos are growing within the yellow ball, which will give us a hint to see how these stars of different masses actually form in the first place. Last year, there were several teams that used ALMA to study the growth of planets within circumstellar disks around stars that are a mere like hundreds of light years away, young stars that are not very, very massive stars, and they're reasonably close. ALMA can probe the details. These are artist concepts over here, and basically these are two systems where the motions of the gas in the disk have been used to infer the growth of, I think, something like 3 gas giant-sized planets in one of these systems, and something comparable in the other. So what's exciting about that is we're actually starting to see where planets form. Some of you who have been following the search for exoplanets may know that not all the planetary systems we're discovering look like our solar system. There are some solar systems with huge gas giants orbiting their star in just a few days that are very, very close, unlike Jupiter in our solar system, which is very far away. So we'd like to understand how different kinds of planetary systems can form. Other questions being pursued, hot off the presses from just within the last couple of weeks. A team has studied both a jet and an outflow on very small scales. I'm sorry, I didn't have time to put a scale up here, but basically what they found is that these different features are actually produced or are launched in different places in the disk. So the jets that we observe in like near-infrared wavelengths may not be connected directly to those larger scale outflows that we observe. Moving along to where astrophysics meets astrochemistry. So I had to give a word about this. ALMA has these wonderful, very large bandwidth receivers that can be configured both to doing dynamical studies. So you get maybe fewer lines, but very, very high spectral resolution, or it can be configured to give you a line forest, to get a lot of different lines within that bandpass. So the National Radio Astronomy Observatory has this great web tool called the Splatalog, where you can actually use this tool to figure out all the different kinds of lines you can get in a particular configuration for ALMA. So this is a great instrument for both astrochemists and astrophysicists to use. So finally, I wanted to end on the telescope that I sort of began with, because this telescope is near and dear to me. It still exists. It got a facelift a few years ago. That's my family and I standing in front of the remains of the old dish. Now it has a bright new shiny ALMA dish. Doesn't have great resolution, but it's got state-of-the-art spectrometers, receivers now, and so it's still doing very, very useful work. It's run by the University of Arizona's Astrochemistry and Radio Astronomy Lab. So there is an astrochemist named Lucy Zuris who has a laboratory there where she does a lot of studies of different molecular line frequencies. And so they're working together, the astrochemists and astrophysicists working together to use this dish now in concert with the higher resolution that's capable with instruments such as ALMA. So one of the things that was really cool, one of my sons there was pointing to the name of myself and my spouse. Some of the people who got to sign segments of the old dish were really the pioneers in microwave astronomy, so we were really, really honored to get a chance to sign the segment of the dish. My spouse was an operator at the time that I was using this telescope for my dissertation. So he was head of operations. He's sort of the engineering background. I'm the astronomer. So we both got to sign that dish. And I think that's probably where I'd like to stop. It's been about an hour, maybe a little bit longer that I've been talking now. Take questions. Thank you. Yes. So in fact, you need the outflow to get the inflow, and it's very elegant. What happens is the magnetic field actually gets twisted in the disk, and the charged material sort of gets flung out and drags some of the neutral material with it, and in that flinging process, it slows down the spin of the inner disk. Some of the details are obviously still being worked out because now we have the resolution to actually explore where these outflows are launched. But that's the idea. The idea is that most of the star builds up by infall through the disk. So what I didn't get a chance to mention was that in these larger envelopes that collapse down through gravity, material falls onto a disk, but then before falling onto the star, it goes through the disk onto the star. So you have the bipolar outflow ejected in one direction and the material coming in through the disk along the perpendicular direction. So most of these outflows are more or less perpendicular to the disks. Thank you, that's a good question. Thank you. Other questions? Yes, Richard.
I have a question about citizen science.
Sure.
As someone who regularly trains undergraduates in my lab, it's hard enough getting people who have years of courses related to my research, to understand and get the details right where they can reproduce things reliably. How do you handle that when it's basically random individuals on the internet that are finding these young balls?
It's the crowdsourcing. So there are quality checks that experts go through subsets of the data and check these things. The frequent users do an excellent job. So there are a lot of studies, and on the Zooniverse site, there are meta-studies where dozens of papers where you could read about the quality checks for the citizen scientists. And, basically it's the wisdom of the crowd. Even if there are outliers, that's why we tell people, don't be afraid to make measurements or to make mistakes, because basically we have enough participation. People in general are good at spotting patterns in ways that machines aren't. So even if you don't have specific knowledge, good knowledge about a field, you still have the capability to spot patterns. So the tasks we ask them to do are tasks that everyone is good at doing. Of course, some people get more and more interested, more and more involved. We give them resources so they can conduct their own research, so they can, look into various things that they're finding at more depth. But for the most part, the sorts of tasks that people do, people are really great at doing. The animal projects, some of the most popular ones are the candid cameras. So they have candid cameras set up, and you've probably seen some of these if you watch Planet Earth and various shows on TV, where basically people are looking for animals in images and classifying the animals, against lists, which are being used to basically figure out ecosystems and how animals migrate and how those patterns are changing with time. The other thing I wanted to mention, which I think is particularly cool, are the disaster relief projects that spring up when a disaster sadly occurs. Zooniverse partners with the Planetary, I think it's called the Planetary Response Network. So several years ago, for example, when there was a large earthquake in Ecuador, some of you may remember that, what they did was they offered, on the Zooniverse site, they offered up before and after satellite images of the regions where citizen scientists were identifying road blockages and things like that, and that information was being used by the ground crews to know where and how to deliver aid. So this is another way to participate. If you can't give money or you don't know where your money's going, if you can't hop on a plane and go down and give relief in person, there are ways of doing that simply through participating in one of the disaster relief projects. So yeah, but quality control, yeah. The other thing that that some of these projects have been used for is in machine learning. So the identification of those bubbles in the Milky Way project, there was a paper written that actually used the citizen science classifications to train computers and to iterate on that and actually come out with a better bubble catalog because of the combined citizen scientist and machine classifications. So one of the things we were talking about at the very beginning here is some of the upcoming missions in astronomy are going to have so much data that it's too much for just people to handle, too much in some cases for computers to handle. So by training computers to be better at spotting some features and some anomalies, they'll be able to cut through some of the incredible amount of data coming down the pike. There's a telescope being built in Chile that is an optical telescope that's going to do a complete map of the entire southern sky every few days and get images of very, very faint things and track how things change in the sky. And there's going to be more data than any human being can handle. More questions? Yes? Yeah. No, there is, in fact, you can look up, there are something like 200 molecules now known from the spectrum, from diatomic on up through many atoms. So there's even been, I can't remember which of the amino acids that has been discovered or where, but very complex chemistry that goes on. So I know the hydrogen, okay, so my astrochemistry is incredibly minimal. I mean, I've had classes like 35 years ago. So, once I know which molecules are good for studying what I want to do, I use those molecules. But I know that the hydrogen molecules are via grain interactions, or hydrogen molecule, the molecular hydrogen tends to be formed on grains, carbon monoxide through gas phase chemistry. The polycyclic aromatic hydrocarbons, there's a lot of work going on in that field right now. There are some molecular chemistry that can take place in the extended atmospheres of old stars, of evolved stars. The conditions are right for some of that. But there's a lot out there. And how that gets processed and survives cosmic rays and radiation and everything, that's an exciting field. More questions? Yes, back there.
So, in this slide, you said Arizona gets an ALMA telescope. Does that mean you're a part of the ALMA system, or simply a telescope of the same?
Well, actually, no. That's a great question. No, we're not like doing very long baseline astronomy with this. At least not at the present time. In fact, this telescope is now not run by the National Radio Astronomy Observatory anymore. They run ALMA. This telescope used to be run by NRAO. It's now run by what's being called the Arizona Radio Observatory. So, yeah, I'm sorry. No, this isn't being used in conjunction with, like, for example, the network of radio telescopes that I'm told came out with the press release today on the imaging the starlight passing the black hole at the center of our galaxy. I was driving here from Naperville, Illinois, so I missed all of the excitement today.
So, do you see a future for a long baseline for the kind of work that you're interested in?
Well, see, it depends, because there's resolution and then there's imaging. So you can get very high resolution with long baselines, but to get a really good image, you need to fill in. So you need to be able to move those telescopes and sort of fill in the gaps for an interferometer to do its work. So for just high resolution, you really need the baseline plus the filled-in aperture to figure out what's going on in some of these structures, because they're so interconnected. The black hole at the center of our galaxy is so far away that that's a really small image. You get to a point of diminishing returns where you're imaging. So tonight I talked about both really large-scale surveys as well as some of the more detailed surveys. It's always a trade-off. You either do a large survey and get a whole lot of objects and then do statistics to figure out some of the interesting properties, or you observe things in their gory detail. You don't do both. ALMA is not going to be mapping out the plane of our galaxy. It's going to be a great instrument to study specific objects. It's great at the level of like circumstellar disks, places where the outflow is being launched, and some of these yellow balls where we can actually study infall onto stars. But as far as the very long baseline interferometry, I'm not seeing how it's going to be very useful for that. I think that where that's useful is for things that are really far away in the universe, like black holes, for example. Great question. Thank you. More questions? Yes? Yes. So when I say C, I mean the interferometer makes an image in kind of a complicated fashion, but it can actually study the motions of gas, how the gas is moving in those disks. So there are several systems now with stars that have disks around them that have been studied so that the velocity structure has been mapped out in enough detail to figure out how much material is accumulating in various parts of the disk. It's a remarkable thing that we can actually do that. So for example, one of the interesting questions is, when you look at all these exoplanetary systems, there's a wide array. They're completely diverse. There are some planets, there are some systems where you've got a planet orbiting 2 stars, or a planet orbiting in a system with 4 stars. That one was discovered by citizen scientists, by the way. Or you've got planets on all sorts of weird orbits, like these really big Jupiters that are orbiting like, well within the distance of Mercury from our sun, that are orbiting really close. How do they get there? 50 years ago, we thought that all the little rocky things condensed out of the hot protosolar nebula closer to the star, and these big gas planets formed way further out. But now, where there's evidence that some of these big planets can actually form closer. So the idea is, do they form closer, or do they start further out and maybe get dragged in as all of this material is forming? So that's something we would like, because we would like to understand, how basically unique or not our solar system is. Of the 4,000 or so extrasolar planets that have been detected around other stars, just under a third of those are Earth-sized or slightly larger. A type of planet we call super-Earths or super-Terran that may have, among other things, may have large oceans, but there may be a lot of rocky planets out there, so we'd like to understand how they form and how many of those planets might have conditions suitable to life. And by the way, there's another telescope that hopefully will be launched in 2021 called the James Webb Space Telescope that's actually going to be able to study the atmospheres of planets orbiting stars that are relatively nearby. If you remember, and look for biosigns, look for signs of possible life on those worlds. You remember I mentioned these little red dwarf stars that are ubiquitous. There are some that are very, very close. Well, there's a system 39 light years away where there's 7 Earth-sized planets orbiting one of these cool little red dwarf stars. The system is called TRAPPIST-1. They orbit, even the 7th planet orbits far closer to that star than Mercury is to our sun. It orbits the star in 21 days. All of the 6 of these planets, we have information on both the mass and the size, so you can calculate an average density. 6 of them are there's good evidence, are rocky worlds. 3 of those are actually within what we would call the habitable zone, the right distance from that very cool dim star that liquid water might exist on those planets. So it's really exciting. So within a few years, we could know whether those planets have any kind of appreciable atmosphere. So some of you here in the audience certainly might be alive when we discover signs of life on another world. I mean, we may never discover it if there's certainly there's a big gap between going from a planet that looks like it might have conditions for life to an inhabited world. But some of those questions, if life is frequent, we do have the ability to discover it on nearby planetary systems within the next 10 or 20 years. So it's exciting. I think it's exciting. I grew up with Star Trek, Yeah. Did you have a question? Or no, just, yeah. Well, that's something else that's cool to be at the Adler Planetarium. We used to have this series called Real Science, spelled R-E-E-L. where we would watch, we would invite the public to watch science fiction movies with us, and then we would discuss them, and I don't mean trash them, I don't mean pick apart what's wrong, pick up on some of the themes and then explore, you know, what the real science is like. Because in my lifetime, I know I've seen so many things that were almost prophesied in Star Trek, you know, be developed over the years. So it's really, really cool to work for Planetarium. Anyway, is it time to wrap things up, I guess? Or was it?
If not, please join me in thanking Dr. Wolf-Chase.
Thank you.